Welcome to This Explainer. Okay, so today we're looking at how a delicate, ancient Japanese paper folding art is actively solving one of modern spaceflight's biggest engineering bottlenecks. I know, it sounds a bit like science fiction, right? Blending a traditional craft with cutting-edge aerospace engineering, but it is literally happening right now, right above our heads. We're going to unpack exactly how engineers are using this technique to totally change the way we explore the cosmos.
Let's kick things off with Section 1, an ancient art in orbit.
So think about the core tension space agencies face every single time they launch a mission. It's this constant battle between the massive ambition of what we want to do in space and the sheer, unforgiving physical limits of actually getting there. I mean, if you think packing a car trunk for a long family road trip is stressful, try packing a rocket. Space travel is incredibly constrained. Rockets have practically zero spare room in their fairings. Yet the modern satellites we rely on for communications, observation, and deep space data, they require massive solar arrays and giant antennas to actually function once they get up there. You simply cannot launch a fully extended 50-foot antenna into orbit. It just doesn't work.
Well, engineers recently proved a mind-blowing solution in space. We're talking about a staggering 25 times expansion. No way, right? But they actually managed to take an ingenious, complex antenna structure, pack it down into a tiny, unassuming little box, and launch it. And once it reached orbit, that tightly packed box expanded to 25 times its original size. Just imagine a package the size of a toaster suddenly unfolding into something the size of a dining table, completely on its own, just floating there in the vacuum of space.
So how do they do it? This incredible expansion relies directly on the principles of origami. By using traditional Japanese folding techniques, engineers can perfectly pack vast sheets of material into incredibly compact 3D shapes. You know, when you fold paper, you're essentially programming a flat surface with geometric instructions on exactly how to collapse and expand. Space agencies are taking this exact same concept, swapping out paper for advanced aerospace materials and using it to safely pack and flawlessly unpack massive structures.
Moving right along to Section 2, the Kakushin Rising Mission.
All right, let's see how this goes from a brilliant theory to a proven reality. On April 22, 2026, the Kakushin Rising mission blasted off into the sky from a launch pad down in New Zealand. What we're looking at here is the actual view from the upper stage of the rocket, looking back as the first stage falls away towards Earth. This launch marked a huge, tangible success for a collaborative effort between the Japanese Space Agency, JAXA, and the commercial launch provider, Rocket Lab.
To really give you a sense of scale, let's look at the vehicle that made this whole thing happen. The Rocket Lab Electron rocket is a highly specialized, highly efficient machine. It's actually relatively compact at just 18 meters tall, and it's specifically designed to cater to the booming small satellite market. And you know, this wasn't some experimental test flight. This was the Electron's 79th flight, proving it's a super reliable workhorse. About an hour after liftoff, it flawlessly delivered its payload into a low Earth orbit at an altitude of 540 kilometers. It's such a versatile platform that its specialized HASTE version is even used for suborbital hypersonic testing. Now, it really helps to put this launch in its proper historical context. The Kakushin Rising mission didn't just happen out of nowhere. It was actually the second flight of JAXA's Innovative Technology Demonstration Program. It followed up on the RAISE and SHINE mission from December 2025, which launched the RAISE-4 satellite to test out various new technologies. This steady, step-by-step timeline really shows a committed, systematic approach to proving these next-generation technologies in actual space conditions.
So, what was actually packed inside the fairing of that Electron rocket on April 22nd? Well, the Kakushin Rising mission carried a really diverse cargo of 8 different satellites. You had small educational satellites designed to train the next generation of aerospace engineers. There was a dedicated ocean observation satellite, plus a demonstrator testing out an ultra-compact multispectral camera. But the absolute star of the show, the payload really pushing the boundaries of mechanical engineering, was that brilliantly folded origami antenna, just waiting patiently in the dark to expand to 25 times its size.
That brings us to Section 3, the engineering of space origami.
Okay, now that we know about the mission, let's look at the actual mechanics here. Why are the world's leading space agencies turning to centuries-old paper folding techniques for multi-million-dollar spacecraft? At its core, space origami is exactly what it sounds like.
It's the strategic use of traditional folding patterns to compact incredibly large, vital structures. We're talking giant communication antennas, expansive solar panel arrays, and massive heat shields. The whole goal is to tightly pack these wide surface areas into tiny, manageable volumes for the rough ride to orbit, and then just rely on the physics of the folds to auto-deploy them once they hit the weightlessness of space. It's elegant, simple, and incredibly effective.
But you know, it's not exactly as easy as folding a paper crane on your desk. It's a real balancing act. On one hand, the logistical pros are immense. You get drastically reduced launch volume, which saves literally millions of dollars. The structures are incredibly lightweight. And because the unfolding relies on simple geometric mechanics, instead of thousands of heavy, complex motors, it's highly reliable. On the other hand, the challenges are brutal. The unforgiving vacuum of space doesn't care how beautiful your fold is. These materials have to survive intense solar radiation, wild temperature shifts from blistering heat to freezing cold, and the entire structure absolutely must achieve flawless deployment on the very first try. There's no mechanic up in orbit to unjam a stuck hinge, right?
Which leads us to our final part, Section 4, the future of space folding. So now that the Kakashin Rising mission has proven this technology actually works under those extreme conditions, we've got to ask, what does this all mean for humanity's future off-world? The absolutely crucial takeaway here is that space origami is not just some neat parlor trick or a quirky gadget. As the source material makes incredibly clear, this is a major, foundational asset for all future space exploration. The ability to launch small and expand massive is basically the key that unlocks deep space travel. Without this capability, we simply can't bring the necessary infrastructure with us to other planets.
Engineers are already taking the lessons learned from this 25 times expanding antenna and applying them to self-deploying structures for future lunar and Martian missions. Actually, the source specifically mentions the development of inflatable houses for the moon. Literally. Just imagine landing a tight, compact module on the lunar surface that, using these exact self-deploying principles, unfurls into a sprawling, multi-room habitat for astronauts.
So, I want to leave you with this final thought to ponder. We have just witnessed a massive satellite antenna folded into a tiny box and successfully deployed in orbit. As we prepare to return to the moon and eventually set foot on Mars, the sky is quite literally not the limit anymore. It really makes you wonder, if we can achieve a 25 times expansion today, what colossal, awe-inspiring structures are we going to unfold on the surface of Mars tomorrow? Thank you for joining me for this explainer, and keep looking up.